Okay, so we have 5 stages: preprocessing stage, compilation stage, then assembly stage, linker stage, and then execution stage. At the end of this stage, you have your final exe files, like executable files. Well, exe is an extension for Windows. Basically, what you have is a program which can be executed by your computer. If you open it, it runs. That's it. Like app.exe or like game.exe. Similarly, you have other extensions for other platforms like Linux. Well, Linux doesn't give you any extension after the name of the file. It's just the name of the file. It's just called app or game. There may be some extensions that Linux can identify as executables, but normally when I'm compiling my code in Linux, it's usually the name. But anyway, in this stage, we have executables that can be run directly by opening them. So how do we get here? First, we begin with our source files that are either .h or .cpp files. .h files are header files and .cpp files are your implementation files. When you run them through the compiler, first goes through the pre-processing stage, which deals with lines that start with hash, like hash include or hash define or ifdefs. It deals with all these lines. For example, with hash include, it will replace the line hash include whatever file is in quotes with the actual file contents, and it spits out a file with an extension .i, but it's basically a CPP file. You will actually see this in just a few moments because I'm going to write a very simple app to demonstrate all these stages. And then we move on to the compilation stage where the actual compilation happens. It takes in the CPP file or the .i file, and then it checks for syntax, sees if you missed a semicolon somewhere or if you forgot to close the curly bracket, things like that. And it will generate an output file, which is human readable assembly code. And this assembly code contains assembly instructions, obviously. And then it moves on to the next stage, which is the assembly stage. It converts all the assembly instructions to a binary format, which is of the form or of the extension .o, right? So this .o file is not an executable by itself because it still needs to like connect to other symbols which are in other O files. It will make sense in a bit when I explain this with code. But basically what happens is in the next stage, in the linker stage, it takes a bunch of all the .o files that are related, and it looks up all the symbols, it resolves all the dependencies, and like it produces the executable after doing all the linking, right? And then finally we have our executable, which can be run and which can be executed. Okay, let's quickly do an example to see all of this in action, and then we can finally get to automating all of these things with CMake. Okay, so what we're going to be doing is we're going to make a simple library, and the actual application we're going to make is going to be a separate app, and this application will link to a library. Let's say this library has very simple functions like maybe some math helpers, some math helpers that the application uses, and after linking to this library, it produces the actual executable, maybe like app.exe. Well, the reason I'm doing it this way is because this is normally how it's done when you're dealing with game engines, because at the end of the day, your game engine is a library that you ship or you publish to your users who are the game developers. They will link their game application to your game engine, and that in turn will produce an executable, which is like game.exe or something. And when the players, they will open game.exe and then they'll play the game, right? So as engine developers, what we're going to be making is a library, right? A library which the game developers will use and link against. All right, so let's see all of this in action. I'm going to open up my terminal, and I'm going to cd into my personal folder, and let's make a directory called, I don't know, like compile example or something, and compile example cd, and tmux, open up bin, right? So we're in the folder now. First, let's create the library, right? I'm going to call it lib.h, and this is going to be the header file. Let's add the header guard, pragma once, and let's keep it simple. Let's just make a very simple inline function that takes in 2 different variables and adds them, right? Int a, int b, and open close, it just doesn't need the semicolon. And all it does is just returns a and b, right? That's it. Actually, you know what? Let's make it a little more interesting. Instead of the free function, let's make a class instead, and let's do add, and let's make the constructor. And the constructor is going to take in int a and int b, and let's make it public so people can actually use it. And then let's define our member variables, int member variable a and int member variable b, right? Let's initialize them. Okay, so if you don't know what this is, it's just basically like an automatic way of initializing. It's just the same as like making it 0. Like for known data types, the compiler can automatically initialize for you. In this case, I think all numbers have a default value of 0, if I'm not wrong. Anyway, so let's just initialize it like this. And now here we can make use of the initializer list syntax to store those values from the constructor right away. So let's do that. MA, number variable B, yeah, and now, yeah, so we've defined the constructor which takes in the values and then saves it, right? So what I'm making here is something called a functor. It's basically like a lambda. It will make sense once I'm using this in an actual application. So because this is a library, I'm going to be linking this library against a different application. And then when we do that, you'll see how it all works. But just think of it like an object that has an operator that can be called, right? So let's define the operator. The operator is going to return int as well, and that's it. That's all the class declaration looks like. And just to make things more interesting, let's add another function called subtract. Sorry, another class called subtract. It's going to look the exact same. Let's see. Yeah, it's going to look the exact same. And now we have done the header file, we've done the interface file. Now let's do an implementation file, right? So I'm gonna make another file and call it an implementation file, lib_impl.cpp. You can name it whatever you want, but just to make it like readable, I'm gonna name it lib_impl. So let's include the header file, and then let's see. Yeah, we only need to define the operators. So let's int add operator. And let's write the body of the operator. It's going to return m_a plus m_b. Yeah, simple, right? That's all it's going to do. And let's do the same for subtract as well. But instead of a plus sign, we're going to do a negative or minus sign, right? Okay, so we have our header file and we have the implementation file, right? Simple, right? So, well, we actually have the source files here, and now we're gonna have to compile them, right? Now, if you remember, the first thing the compiler does is pre-processing, right? So the pre-processing stage, it will take in the source files, and it will expand all the macros. It will like resolve like all the lines that start with hash, and then it will make one big file, which is essentially a CPP file, but the extension is .i. And let's see, let's do that with G++, right? G++. Oh, by the way, G++ is just a C++ compiler for Linux, I think. There's also one called GCC that I see people using for C, but I don't use G++ or GCC because normally when I'm making a C++ application, I'm using CMake to automate all of these things, which we're going to do in this video if I stop my rambling and get to the point. But yeah, so G++, I'm going to do help because I don't know how to use this. So essentially what we want to do is like pre-process. Yeah, so it says like this flag, pre-process only, do not compile. Yeah, so the flag that we need to use is E, and also here it says like, oh, I knew this one. So if you want to output the file, the flag you need to use is .o. Actually, let's make another pane here. And yeah, so G++, I'm going to use the flag E to pre-process. And we're gonna use our implementation file, right? Like lib_implementation.cpp. And the output is gonna be lib dot, the extension I told you was I for preprocessed files, right? So yeah, I think it did the job, and let's go back and see the file, right? Well, let me quickly close all of this and open the I file. All right, so take a look at this file, right? This is just a CPP file. It looks exactly like a CPP file. And this whole thing is what's known as a translation unit. Like, this is going to be really important later. So I'm going to write it down separately. Translation unit, right? So a translation unit is what you get when the pre-processing stage is done, and it produces like one file, one huge CPP file, which contains all the things that are related, like all the header files and all the macros that are needed. And it like jams everything into one CPP file. So, okay, so that's called a translation unit. And this is very important when we're going to be doing CMake. You will understand it better intuitively, like when we get to CMake. But yeah, so we're done with the pre-processing stage. We got this I file. Let's move on to the compilation stage. If you remember in the compilation stage, after the compilation happens, it just produces one .s files, because like this is the assembly file. like which we can produce using G++ again, G++ and preprocess. Yeah, so I think this is the flag, compile only, do not assemble or link. Yeah, that's what we need. We need to compile, so let's do it. Let's use the flag, and this time we're going to use the lib.i file, and then the output is going to be lib.s, right? All right, so let's take a look at lib.s, and would you look at that? It's a very beautiful looking assembly file, although I do not understand a single line in this file because I never bothered. Maybe I will in the future. But anyway, so this is done. Like we've finished the compilation stage and produced an assembly file, right? Now in the assembly stage, if you remember, I told you that it's gonna produce a .o file, which is not linked yet, but it's just the compiled output. It contains all the implementation instructions from one translation unit, right? So if we have a different translation unit, if we have a different library, it produces another .o file. If we have another library, we can do the same and produce another .o file, right? So in the linker stage, we can like link to different .o files and then produce the final executable, right? So let's produce the .o file, right? So let's go back and G++, and this time we're going to use this flag, compile and assemble, but do not link. Yeah, so we're not doing the linking yet. We're just going to compile it, right? So yeah, we're going to use the libs file, which we got in the previous step. And the output this time is going to be .o, all right? So like, remember I told you that the output file, like the .o file, is just a binary file which contains like machine instructions. But, and so if I open it, it should contain like binary, right? It's a bunch of gibberish, like all these hexadecimals. Yeah, so we've got the O file. All right, so that's it. Yeah, we've compiled our library. And so we actually don't, let's delete all the unnecessary things that we don't need anymore. Like the preprocessed file and the assembly, we don't need it because we got the final compiled binary. We actually don't even need the CPP file anymore because when you're shipping your library, all you do is provide a public header or like an interface file and the .o file, which is your binary, which contains all the implementation instructions. There's one sort of like a little nuance. A bunch of .o files can be grouped together and they can form something called a static library or a dynamic library, right? The static library in Linux has an extension .a, and I think in Windows it's .lib. I'm not really sure, but something like that. And the dynamic library in Linux is called SO, which means like a shared object file or something. It's a shared library. And in Windows, it's called, I think, DLL, Dynamic Link Library. And so like basically, like when you're providing your users with your library, like distributed library, all you do is provide .h files and .a files or .so files or .dll files. These are the implementation instructions, binary formats. And this is just a header file that they can use to like write code, like human readable code, right? So this is something that I want you guys to remember. It will give you the exact intuition needed to make targets in CMake, right? Yeah. So yeah, so let's just proceed. We've done this assembly stage. We got the object O file. And now let's move on to the client side, right? So let's assume you made your game engine and then you you distributed these online and somebody is using these to make their game, right? So, so let's say the game is called app.h or app.cpp, sorry. And I want to use this library, right? I want to use this library and include, I'm going to include the library and I'm just going to make it really simple here. Int main, the main function, and return 0. And if I want to use the library, I'm going to take a look at this, right? So this is what's so beautiful about C++, right? It has like a really cool interface file. You don't need to like write like all these detailed documentation to let your users know what's inside. It's just you can just open the header file and just take a look at the functions there, and then you can just use it, right? Let me quickly make an add object, add, and let's instantiate it. Let's make I don't know, 32 and 98. Well, actually, let's use some actual L values instead of this. Int A equals 32 and B equals 98. And in here, let's use the L values instead. right? So we got this, right? Now we can just print these std_cout and add. Okay, so now I'm gonna call the operator function, right? Like the operator method, because to actually evaluate, we're gonna be calling the operator. If you remember, this operator is what does the actual calculation. When the object is just initialized, it only takes in the values and it just stores them. It stores them in the object when it's initialized, and the actual operation, like the actual calculation, happens here, right? When you call the operator, right? This is exactly what a lambda is, or like or a callback is, because like let me write a lambda to demonstrate. Like auto add lambda equals, let's assume it's going to capture A and B like this, and in the body of the lambda, it's going to do the exact same thing, A plus B, right? So this is the same exact thing. Like this lambda and this add is the same exact thing. So let me print them. Let me print them to show you what I mean. Lambda, let me add a new line, and let me actually add a divider so it's all clean when it prints things out. Okay, all right, so we've done this. So yeah, so this is called a functor. Basically the purpose of a lambda or a functor is like you instantiate a tiny object with some data, and then you call it at a later point with some function body. In this case, the function body is just adding up to two values that it stored previously. And this is very useful because like when you want your program to instantiate some values at one point, and then when something else happens, like maybe when an event occurs, maybe when somebody clicks on a keyboard or like presses a key or clicks on the mouse, at that point you want your functor to execute the function body. You can just use a functor, right? That's basically what a callback is, right? Yeah. So all right, so this is not about callbacks, but anyway, I thought it's something cool that I realized when I was learning C++, so I thought I'll share this example. Right, so we have this. We have our application that uses the library, right? And now we want to do the linking. Well, we have to compile this app.cpp first, so let's quickly do that. Well, we don't have to like go through all the individual steps this time. We can just directly use G++ and directly go to the compile step. G++ -c, and the file that we want to compile is app.cpp, and the output is going to be app.o, right? Awesome, so it's done. So we got the binary, and we got the library's binary as well, right? So let's link them together and make an executable, right? So G++, so if you want to link, I think it's just, you don't need to pass any flags. You can just do it directly. Let's link app.o and lib.o. And the output this time, let's call it app. Remember, in Linux, it doesn't have any extension, unlike Windows, which has like a .exe. So let's do this, right? So we have our application, our executable. Finally, we can just run this application and see what happens, right? Okay, so you got 130 and 130. Yeah, that's it. That's it. This, like, we successfully linked to a library, and then we got the output executable that we can share with our users to run it in their computers, right? That's it. So this is how the compilation process works. And now let's automate all of these things and use it in a really complex setting, like a game engine setting or a game engine project, and see how CMake helps with all of this, right?